Welcome, everyone. My name is Ryan Lee. I'm a cloud infrastructure engineer at 10th Magnitude, and today I'm going to be introducing you to Docker and containers. Welcome. I tried this Docker lunch and learn kind of format before. Didn't have the impact that I was hoping because I failed to properly introduce Docker and instead talked about all of the infrastructure and orchestration tools that you would do if you were using Docker in production, without explaining why you would want to in the first place. So we're going to try again, and this time I'm going to introduce Docker, why it can help, and why you should use it. So simply put, a container is a single process that's distributed with its own isolated file system, and that contains everything that the process needs in order to run. Containers are not a new idea. Other companies and projects have been approaching the same problems for years. Linux containers, FreeBSD jails, OpenVZ, they've all approached the same problem in different ways. So Docker kind of hit the right mix of ease of use, developer friendliness, powerful capabilities, and if I'm being candid, probably got some major cool points for being developed right about the beginning of the DevOps kind of community. So containers themselves don't run on multiple systems. They're not distributed by nature. You can run multiple copies, and that's the way you should do it, but basically they're just like a service on a traditional VM. One service, one container, runs on one VM. So they're ideally multiple instances of the same app distributed over multiple machines, rather than one big app like a Beowulf cluster or a compute cluster. So let's talk about the VMs that you're familiar with and the differences between them and the containers you might not be. So VMs, they're emulations of server hardware. So it's hardware level virtualization. So they run a traditional operating system. That operating system has a kernel, a bootloader to boot itself. It's got its own network stack, user land utilities, libraries, package managers, what have you. They're self-contained. They have everything that apps need to run and then some, including maintenance and update processes. So the hypervisor gives a VM a reserved resource, like a reserved number of CPU cores or a reserved number of RAM, or amount of RAM, a reserved amount of disk space. They're suitable for running multiple services and applications all in one box. If you're taking the microservice approach, then you're probably not doing that, whether you're using containers or traditional VMs, but they're suitable for it. And they've got those mechanisms for like WSUS for updates and patching, and Active Directory for configuration and things like that. And for actual state management, from a flat VM to something with state, you use configuration management, or you can log in with a GUI, or you can use a scripting language to settle that up for you. Docker containers, though, they're just networking, libraries, storage, and applications. They do not have a kernel. They share the kernel with the host, and that host is what the Docker engine is running on. So these are operating system level virtualization. They do not present virtual hardware to the container. It doesn't need it. It doesn't care about it. It just needs something. So they're allocated resources rather than reserved. So they get slices of available resources. So say the VM that they're running on has 8 cores and 32 gigs of RAM and a terabyte of disk space. They are allocated slices of that rather than reserved that amount. So you can over provision pretty easily. They're much smaller in size. For example, an Nginx container built on the Alpine Linux distribution is 17 megabytes. And that contains everything that Nginx needs to run. You can pull it down on any machine that supports Docker and run Nginx. So it still requires a host operating system with a bootloader, a kernel, storage, networking, etc. But there are operating system distributions that are designed just to run Docker and the Docker engine and the associated networking and storage. So they're purpose-built just for running containers. They're also much more limited in scope. While you can run multiple services in one container, that's usually not best practice. You want to have very clear definitions between, or distinctions between the containers. So, for example, you would have a DHCP server in one container. You would have a load balancer in another. You would have a web server in another. And then if you wanted to scale, you would create multiple instances of those containers, those services. They also start extremely quickly. They start as fast as whatever the containerized app you're running is. In the case of like HA proxy, it's less than a second. You want a new server or a new instance of HA proxy, it takes less than a second to distribute and provision. The way, I'll get a little technical about how Docker distributes itself. So a container is just a collection of layers. And each layer contains the diffs between what happened to it at that time. So like Ubuntu will distribute an Ubuntu base image. And when you're creating another Docker image from that, you reference that as your base. And then any changes that you do are just building on top of that. So if you install Nginx and copy over a configuration file, that's another layer. And if you send that container, or if you send that definition to somebody else and they rebuild it and they already have the Ubuntu base image, it doesn't need to download it again. It understands that the only thing that it needs to do or download is the diff between the upstream Ubuntu image and the one that you created with Nginx and a configuration file on it. So it makes provisioning really fast too. So why containers? Well, they're inherently scalable. There are a lot of approaches to containers that you can do with traditional VM-based infrastructure. You can run scale sets. You can provision with configuration management and get a state. You can get immutable images with something like Packer and spin those up. The benefit to Docker is it's so much smaller and it's so much faster. And it's much easier to use in a development environment. And then that same image that the development team creates as part of their pipeline process is eventually the same image that gets promoted to production if all the tests pass. So it's the same all the way through the pipeline. There's very few internal moving parts to a container. You don't have to worry about update systems. Like you're never going to run WSUS in a container. You won't even run an SSH server in a container. You probably don't need to do logging inside of a container either, because logging services are able to hook into the output of a container and ship that to your logging system. So all that's really in a container is your application code or your application package and whatever's necessary in order to run it. Very, very limited in scope. They're immutable, so by definition, when you load up an image and you make changes to it, and you spin it down and you load up another one, all of those changes are gone. So if you do want to store data, you need to store it somewhere else rather than inside the container. You can use the local file system inside of it as like a scratch space, but any changes are not going to be persisted, which is by design. You've got an identical, repeatable development workspace, and we'll talk about that later. And you've got a clearly defined artifact promotion, which is what I was talking about before, where the development pipeline creates a container, and that same container gets promoted to production eventually. Additionally, Windows 10 and Server 2016, Windows 10 has supported them for a few months since the anniversary update, and Server 2016 has native support for Windows containers. They've managed to take a nano copy, and it's about 300 megabytes. Basically, they took out all the GUI, all the 32-bit support, a lot of other stuff, and it just runs applications. It's suitable for like large amounts of IIS deployments. Though there are a lot of features and roles that it doesn't support, they're working to make that built in. Otherwise, you can use a server core Docker container. It works the same. It starts up at the same speed. It's just 3 gigabytes instead of 300 megabytes. And configuration management, or configuration of the container, is managed with a flat Docker file, which is basically just Bash or PowerShell. It does a single, not necessarily repeatable process, or internal. It's not necessarily idempotent, but if you are going to run it again, you're going to run it against a brand new, fresh Docker container. So basically, your configuration is done once. It only has to work once, and then that image is set in that layer. So benefits to developers. So picture a developer working on app A, which is part of a full stack that includes app B, app C, Postgres, Nginx, Memcached, Node.js, like a lot of stuff, a lot of moving parts. They ravening few too. So how do we ensure that this dev is working in a workspace with the same package and library versions that another dev is using, and make it user-friendly, make the devs not want to quit? So as part of our pipeline, we can build those containers for all the services that I mentioned before. So when an app B developer makes a change that impacts app A, an app A developer, all the tests pass, that container is promoted into Tev or test or QA or whatever environment you're using for that. And then the app A developer can pull down the latest container, which contains the change that the app B developer just made. So handoff between teams can happen in like less than 5 minutes, between a commit, the test passing, promotion, and then the other developer can just pull down the latest container. So that contains everything that app needs to run. You just download it and run it. So those containers are immutable and portable, so developers are not muddying up their workstations. And they don't need to understand or debug configuration management. So if you were building dev boxes with something like Chef or spinning it up via Packer, you don't need to know about configuration management at all, or Test Kitchen, or how any of that works or gets imported. So all they say is, I want the latest or a specific version of somebody else's app, and I want all of these apps to be spun up all at the same time. And I want them, I don't want to have to know how to configure them to talk to each other, because that's all defined in code by people that do understand how that all fits together. So as an app A developer, you don't really need to know how Memcached works. Or rather, you don't need to know how to configure it and set it up. So ideally, the same containers that the developers are working against are already in production. So you don't have to worry about developing against specific versions. Ideally, you're all developing against latest, because that's what everybody else is developing against. That requires a lot of discipline from your developers, so it's not for everybody. But if you can pull it off, this kind of pipeline is super helpful. Something that I forgot to mention for developers is the ease of debug. So what happens is you're developing your code locally, and you want to see if that change has made an effect. So with something like Docker Compose, you can basically stub out a test demo environment. You can say, I want app B, app C, I want my container with app A that I'll populate with code. And I want the latest version of all of these, like Nginx and HAProxy, whatever the full stack needs in order to work, or whatever is relevant to my individual test. And then through the use of volume mounting, you can mount a local folder on your box to a container. So that container contains all of the libraries and whatnot. Oh, do we have a... Scream and yell like worthless Steve. Sure. Yeah, Marcus, I'll speak up. So you can mount a local folder, which is probably where your code is living, onto a container and see your changes live. They did a pretty good demo of this at DockerCon, where somebody was developing a Node.js app and a .NET Core app, and they were able to make a change in their .NET Core app, start up the debugger, which runs the full stack of containers, and actually see their change that they made live. And they could actually debug the code that was in the container through their IDE. So it was really cool. They got a super locked down dev environment that's going to work for everybody with whatever code you're working on and all of its dependencies, including other services. So that was really cool. All right, so before I get into Docker in production, we'll talk about some common things that people usually don't pick up or don't mention when they're talking about Docker. So it's much easier to shoot yourself in the foot and harder to get away with it works for now type solutions in a containerized environment. You'll need to manage storage in a different way. Since hosts are meant to be ephemeral and throw away, and you shouldn't store any data on the actual containers themselves, with the exception of distributed file systems like Gluster or distributed databases like Cassandra. But even then, you need to remove that data from the cluster somehow. And we'll talk about that later. So this means you need to find a way to store all of that somewhere else, like blob storage. However, your app then needs to be able to access it. So we'll talk about how block storage gets exposed to hosts and therefore containers. Networking also requires a new approach. So the way that it works is if you've got a container listening on port 80, a web server, and you have 20 instances of them all on the same machine, they can't all bind to port 80. So Docker will give that container a randomly assigned port. So like 2203, 2204, 2205. You can hit port 80 by hitting the host and then that port, but how do you know which one you're actually hitting, and how do you know which hosts and which IP addresses and which ports actually make up that service? And how do you load balance between them, especially when that list might change in a moment's notice? Again, more on that later. Databases are arguably already the hardest part of a traditional CI/CD pipeline. If you're not able to do a zero downtime database deployment with a schema change to production now, containers are not going to help with that, but they will enable the strategy that can do that. Additionally, if the app that you're aiming to containerize has the concept of a master, but not an automatic consensus algorithm like gossip, you're going to have a bad time, especially if they lose connectivity, which is kind of necessary in that continuous deployment kind of environment. Because you're going to have two or more masters or master members that both think they're the primary, and you're going to have to reconcile that manually. So they need a consensus algorithm, something that's going to help them from getting split brain or split network. And in order to take advantage of a lot of benefits that containers bring, it's essential that you have that in-depth monitoring, health checks, and automated failure recovery and self-healing. Because again, you're not logging into containers ever. If it breaks, it gets killed and you build a new one. If it's a bad deploy or a bad commit, you roll back to the previous version. If you need logs, you look at your logs that are centralized somewhere else. So these containers are completely throwaway and should contain no useful information whatsoever. And everybody has to be in alignment for this to work. So devs, ops, infrastructure, SREs, they all have to take the same approach in order for it to work properly. And service discovery also needs to be a distinct, highly available service, because members of services can change in an instant. So service discovery always has to be up to date. So a push or listening on a queue is preferable to pull. Yeah, so again, we can't rely on things like searching for other members. We need something centralized that says these 20 services, these 20 web servers, this is how you access them, or better yet, this is the endpoint that allows you to load balance between them. Okay, so I've told you about the features that Docker doesn't have, like health checks, well, at least doesn't have natively. Health checks, self-healing, distributed storage and networking, clustering, service discovery, rolling updates, scheduling, etc. So Docker started as a developer-centric tool. But infrastructure, ops, networking, all those teams have had tools develop or spring up around the Docker ecosystem. And especially orchestration tools have kind of collected all of those into a package to make it easier. So like I was talking about before, you shouldn't keep container or data inside of a container, and you shouldn't keep it on a host. Where should you keep it? So it strongly depends on the environment that you're deploying to. Since we're an Azure shop, I'll talk about that. If you can make use of a database or direct access to blob storage, do that. It's probably the safest and definitely the easiest to manage in a CI/CD kind of environment. But if you need stateful data, you're actually hosting that database in a container. Where do you store that? So there are a few ways, and this is probably the weakest part of the container story at this time. There's a lot of development, and I expect that to change pretty soon. The easiest way is to mount some kind of shared network storage on all of the hosts and run one instance or a sandboxed instance of that app. So if you've got 3 database servers, you each give them a folder to put their stateful data on, like an NFS share or something. You shouldn't mount a database on NFS because you're going to have a bad time, but you could. And if you were doing something like key value, then that would be fine. You can also configure your container to directly mount against iSCSI storage. If you want to do that, if you wanted to create 3 block targets for your 3 databases, and they're all in consensus, and that's where they store their actual files, that would also be fine. The current winner is not exactly generally available yet, but it's implemented in the form of external volumes. Basically, there's a driver. You use an open source software from EMC called RexRay, and you can create containerized volumes, which are, again, just file systems. They just don't have an app in them. And those get backed by blob storage. So they follow the container around. If that database dies on a specific host and it gets started back up on another host, that RexRay driver will understand that it's starting, and before it actually executes anything, it will reattach that volume in the same place. So the actual service won't know that it's been rescheduled. It won't care. It's just going to start back up. It's basically like you did a forcible kill and restart a service. So that's the current winner. RexRay, unfortunately, only supports Amazon storage, S3, right now, and like NFS and React. But there are some tools that will allow us to abstract away the blob storage aspect and present it in an S3 compatible way, like MinIO or React both have S3 compatible layers. So I haven't done any testing on the performance implications of that, but I don't think it should be a problem. I don't think there's significant difference between hitting it directly and running it through a compatibility layer. So these orchestration solutions, they also aim to answer networking and service discovery. So how do you manage load balancing across those 20 web servers? All on constantly changing ports and hosts. So a common solution is to use a virtual IP system that's internal to the cluster. So you basically associate a static IP address with a static port against a set of services. And if you hit that address, you get a randomly assigned, or you can control the assignment like sticky or round robin or whatever. You get a member of that service. You can also throw static DNS endpoint above that. So you use DNS as your service discovery, basically. You say, I want to hit this service. This is the endpoint, and I don't care how it's load balanced. Just I want to talk to an Nginx server, or I want to talk to the billing API, and it doesn't matter which instance I hit. So if a container fails a health check from that instance, from that load balanced instance, it's removed from the pool, the container is killed, and another one takes its place. So automated scaling and scheduling are two of the biggest benefits. If you want to go from 20 web servers to 25, it's as simple as an API call or logging into the web UI and moving the slider from 20 to 25. The systems then take account of all of the hosts they have available to them, the resources on those hosts, and they find hosts that are capable of running those 5 extra services, or those 5 extra instances of that web server. So it'll spin those up, and after a successful health check, it'll add those to the load balanced pool. So between 30 seconds to a minute, your new services are actually consuming data or being hit against external services. So combining the automated scaling, scheduling, and health checks, and you get a pretty sturdy automated rolling updates with rollback. So if I update app A from 1.1 to 1.2, and I say I want an 80% quorum, it's going to kill 5 of the existing 1.1 apps, since we have 25 of them now. And it's going to spin up 5 more of the 1.2. And after each individual instance of that container, or instance of that app, passes its health check, it'll kill 1 more of the 1.1 and spin up another 1.2 until the entire cluster is upgraded. If it fails, then it'll just keep trying to deploy that new app. But you can set down like cooldown, so if you fail more than like 3 times in a row, we're going to consider this a failed deployment, and we're going to roll back to the old version, in which case it's just going to spin up 5 more of the 1.1 app. So, best practices. Again, don't log into containers. Kill them and rebuild them. They're cattle. If you need to do a postmortem, that's what your logging system is for. Any information that you might need, you need to configure to be exported to your logging system. Don't make your app require stateful data if you can help it, or try to minimize its impact. If you can't, store it in a database or flat storage. If you can mitigate that, pull data once and use it for the life of the container. Like if you've got runtime environment variables that change the behavior of the container, or like feature flags that change, that's fine. But it's not something you're ever going to have to export, which is the real problem and where it gets hairy. So Docker, that kind of containerized infrastructure empowers you to build super resilient apps if you can take advantage of the features that it exposes. So that means your clients have fewer 4 a.m. outage calls. And instead, they get a nice email when they come in the morning that says, hey, 2 instances of this service broke. We killed them, rebuilt them, and they're all passing health checks. Everything looks good. So anything that you can foresee or anything that can be dumbly fixed by a restart is a good use of health checks. It's important to view your code and the operating system, utilities, and libraries that it requires as one object, one artifact. The code is useless without the operating system, and vice versa. Keep it simple. Containers are hard. Your code and infrastructure should be written for other humans first, then computers. That's kind of opinionated, but I would rather debug a substring method than a 30-character regular expression anyway, or any day. Even if the second one is maybe more efficient or the right way, it's pointless if I don't understand it. Containers should be totally read-only. If they need scratch, it should be mounted as an external volume. You can play with that. If you know that you're never going to need that data, it's fine to use internal storage, but know that it's going to count against the storage that you've allocated for that container. Rebuild often. So ideally, you're going to have automated rebuild and promotion processes all the way to production. So that mitigates security vulnerabilities, keeps you up to date, and allows you to do automated testing of new versions of libraries, packages, and all that kind of stuff, and removes the necessity to have to go back and remove that technical debt by validating new versions of stuff manually. So if you trust your tests, you don't have to worry about a lot of stuff, basically. And specifically your promotion process. Make sure your tests work and that anything that doesn't smell good doesn't get out of whatever environment that it failed on. And run at a high utilization. Unused CPU cycles are a sin, basically, especially when you're paying for specific blocks in Azure. You're paying for specific blocks. You're paying for 8 cores. If you're not using that, you're basically wasting that money. So you can pile up large amounts of individual services on a single host and run it like 50, 60, 70% utilization and save a lot of money. So I'll reiterate that a successfully containerized environment requires you to do almost everything really well. It takes serious engineering talent to run a traditional VM, DevOps, CI/CD environment, and even more to run both, because containers are not necessarily the right answer to every problem. So you're probably going to have to run a hybrid infrastructure where you run apps on VMs that make sense to run on VMs, and containerize those that don't. So there are steps that you can take to make your traditional infrastructure behave more like a containerized infrastructure by using immutable packages such as Packer in coordination with configuration management like Chef. You don't get a lot of the benefits, but it does allow you to take the same approach so that you don't have to manage 2 different completely separate infrastructures. If you're already doing most things right, and your engineers or the processes that they follow have or enforce a lot of discipline, containerization is a huge win and really just super incredible value. So any questions before I do a quick demo of what running a container looks like? All right then. Okay, so in this example, I'm just going to run I'm just going to SSH into, I've got a workstation with the Docker container set up. All right, let's kill you. I didn't care about that shell anyway. It was a cattle. Okay, so I'm logged into my CoreOS box on Azure. So let me pull up my notes here. And I'm going to type in this command, and we're going to talk about exactly what it does. So Docker needs to be run with, or the Docker engine itself needs to be run with root privileges because it's doing things like kernel rewrites and really potentially dangerous networking stuff. So it needs basically system-level access in order to divvy up the resources that it has available to it. So we'll run that with sudo. And then it's just the Docker command. So we're going to run a container. In this case, it's going to be Nginx. We're just going to do a simple web server test. And then I'm going to tell it that I want port 80 in the container to be mapped to port 80 on the host. So when I hit this host on port 80, I'm actually talking to the container. And then I'm going to use the Nginx image that's professionally maintained by the Nginx team in collaboration with Docker. And I'll run the Alpine tag of that image. So an image can have multiple tags that are basically versions. Alpine is just another base, like Ubuntu or CentOS. So it's run that container, and this is just the default Nginx loading screen. So we hit it a couple times, and we can see the output of that container. So since I didn't run it in daemon mode, it's just going to spray all of the output onto standard out. And that started really, really fast. I'm also going to show what mounting a volume or a local directory looks like. So I'm just going to make a directory for Nginx. Oh, I already created that. And then I just have a simple home page set up. So index.html, hello from Docker. So now we're going to run that same command, except I'm going to pass through this directory to Nginx. So sudo docker run map 80 to 80. And then I'm going to pass through this volume to usr share nginx html, which is where Nginx by default looks for its files. If there are already files in that folder on the image, those are just going to be overwritten. And let's make it read-only, because I don't want this container making changes. We'll tell it to run the Alpine version of Nginx. And now we see hello from Docker. So this is the same kind of volume mounting that I was talking about for developer debugging. You just mount the directory that your code base is in. If it's a web app, you just go to the container and hit F5, see what happens. If it's something else, then I guess it depends on what kind of application you're developing. And that's all I've got. Any questions now? I must have done a really, really good job of explaining Docker then.
Very comprehensive.
Yeah, I actually had to cut out a lot of content because it was going to get really just too much, too in-depth for an intro.
Yeah, I guess, like, how would you recommend going about like setting up your own like lab for this, just to start playing around with it? What's kind of like the best way to have at it?
Probably just an Ubuntu VM with Docker installed. Or if you're feeling adventurous, you can install the containers role in Windows 10 and start messing around with Windows containers. The TechNet has a pretty good quick start on how to get that set up.
Hey, I have a question about this Azure Container Service. So, have you used that before? And so, when you create a service like that, what it does? Like, it creates a container, and then how can you, like, if I want to build a web app or something that I want to host in that container, how can I go?
Okay, so the question from Mitesh is Azure Container Service. Basically, what is it and how do I interact with it? So Azure Container Service is just a wrapper. It's an easy way to deploy Docker Swarm or DCOS. Each of those have their own sets of pros and cons. Docker Swarm is fairly immature, and it doesn't answer like complex networking or storage. So DCOS is the product from Mesosphere. Mesosphere is the company that we've been partnering with because DCOS seems like it has the best answer to most of these problems. So describing how you would run a container in that kind of infrastructure is a really big conversation. As a developer, you probably wouldn't need to care about that. You would just run like Docker Compose, which it basically just defines, I want this container listening on this port, and I want it to be able to talk to this container on this port, so I've got Nginx and HEProxy or whatever. And then you would develop inside of that.
What you did here, right? You have a template and you map it to a port.
Yeah, basically. So it's a harness around running Docker manually. So like you could set it up all, just Docker run, map this port to this port, but it allows you to just set up all that configuration in YAML and then run Docker Compose. For running that in production, then that's a whole other can of worms. Good place to get more information is just docker.io and run through the 5-minute tutorial. It'll actually have you, run a container. I think they provide a Vagrant file, so if you need like an Ubuntu virtual machine, you can just install Vagrant and VirtualBox and run through that. But there's instructions in all of this, so you can just follow along if you go to the Docker homepage.
Cool.
Well, thanks everyone for joining. I hope it was informative. Again, I'm Ryan Lee, and this has been an introduction to Docker and containers.